Okay, so we're going to shift gears a little bit, and we're not going to talk about arc and angle measures now. Now we're going to talk about the lengths of the segments and formed by these chords, secants, and these tangents. But before we begin, we want to talk about similar triangles for a minute. Remember, similar triangles occur when you have a triangle and you do a dilation, you make it bigger or smaller. So if I'm just going to copy this over here a little bit, and then I'm going to make this triangle bigger, these two triangles are similar triangles. And what you'll notice is that the angle measures are the same. All three angle measures are the same. I didn't necessarily mean to make it a right triangle, but why not? Let's make it a right triangle. Now, one thing that's true about triangles that are similar is that their sides are proportional. So let's talk about that for a second. Proportional, there we go. Proportional meaning you can write a proportion between them. And you might have seen questions like these in earlier grades. For example, if this side is 3 and this side is 4, and this side is 6, and I want to know what the length of that side is. Maybe you can do something like write a proportion. You can say that 3 is to 4, matching up sides in the smaller triangle, is equal to 6 over whatever that side is, which is the corresponding sides of the larger triangle. And then you would cross multiply to solve that. You'd get like 6 times 4 equals 3 times question mark. And I think if you solved it, you'd get the question mark is equal to 8. So that's kind of the idea we're going to do today. We're going to use some similar triangles to lead us to those equations to write, the proportions and the products to write. I'm not going to spend a lot of time showing you why each scenario contains similar triangles, but I'll just do it for this one here. I have a circle, I have 2 crossed chords. So what I'm also going to do is I'm also going to draw in these 2 chords here. And let's first explain why these 2 triangles are similar. First, you recognize the vertical angles that are congruent? That's good to know. And check this out. See arc BD down there? Arc BD is an arc that has inscribed angles at E and at C. So those 2 angles are congruent. And likewise, if you look at arc CE up top, or just the third angles of triangles being congruent, we know that those 2 angles are congruent. So then these sides, or these triangles are similar, and the sides are in proportion. So if I was to write my proportion, it would be this side here, CF, and if I compare it to side BF, they match up with the other sides, the side EF and the side DF. And I know I got a lot of C's, D's, E's, and F's here, so we're going to kind of clean it up in a minute. But notice what would happen if we cross-multiplied. If we multiply those 2 together, CF times DF. Look in the diagram where that is. Here's CF, and here's DF. What we're doing is we're multiplying together the 2 parts of the chord. And if you look at the other one, where we multiply BF and EF together, when we multiply those 2, we have this chord here, BF, and that chord there being multiplied, or those segments of the chord being multiplied together. So that's kind of the proof, if you will, as to why this equation can be written. So let's kind of condense it a little bit. Let's come up with a couple conjectures. Our first conjecture we're going to call the crossed chords conjecture. And if 2 chords intersect, we're going to say that the product means multiply, right? When you multiply things together, you get a product. The product of the segments of the chords are equal. Real wordy way to say this. If I call this piece A and this piece B, if I break that chord into 2 parts, A and B, and this one I go C and D like that, it's really that A times B equals C times D. That's really what the rule is. So what we'll do is through these conjectures is I'll write down what it is in terms of the words, because I think the language is important. But then I'll show you by recognizing the diagram how to multiply them together. So this is our crossed chords conjecture. The next one is our secant tangent conjecture. And the rule for that is that if a secant tangent are drawn, then the square of the tangent equals the product of the whole secant and its external segment. What? Let me throw the letters in and I'll show you what I mean. Let's call the tangent's length A. And let's call this outside piece here B. But let's call the whole length C. So I'm actually going to do this. Let's throw the B up in there. And let's throw the C up a little bit more. Here's what this really says. It says that the square of the tangent, A squared, the square of the tangent, equals the whole secant and the outside part multiplied together. That's what it means. It's the whole thing times the outside. All right. So in a similar way, we have the two secants conjecture. And that's really like the same as the tangent one that we just had. So what we're going to do is we're going to say that the product of the entire secants and their external segments are equal. That's the wording. Here's the picture. Let's call this piece A and let's call this piece B. Let's call this whole length C maybe. And let's call this whole length D. And you can put the letters any way you want. I'm actually thinking I might just do this. I might call that B and that C just to go alphabetical. So it means that the whole thing times the outside is equal to the other whole thing times the other outside. A times B equals C times D. All right, a couple of the little ones to clean up. This is a quick one here. If a diameter is perpendicular to a chord, it bisects the chord. So if I have a right angle here, so if BC is perpendicular to DE, what that means is that DF is congruent to EF. That's a neat one, that if the diameter is perpendicular to the chord, it bisects the chord. And you can go the other way with it as well. So I'll make this in a double arrow. That if you know one chord bisects another chord, it has to go through the center and be a diameter. Cool stuff. One last thing, and this kind of brings it all together. Tangents to a circle conjecture. If we have two tangents and we draw them from the same point, those two tangents are equal. So segment PA equals segment PB. And we'll even say congruent. We'll make it even a congruent statement. And what's kind of nice about that is if I draw in those two radii, can you tell that I have a kite? And that makes me happy. It makes me so happy, and the day is such a nice day, I'm going to go fly a kite. So thanks for playing, everybody.